Compression ratio is one of the most important numbers in a diesel engine, yet most technicians never calculate it even once. Today I'm going to slow this topic down and actually show you the math behind diesel engine compression ratio using real-world engines, not just textbook examples. By the end of this video, you'll be able to explain compression ratio clearly and calculate it step by step for a Cummins ISB 6.7 liter and a Navistar T444E 7.3 liter engine. And you'll learn how things like head machining, gasket thickness, and piston design can change compression during engine rebuilding, even when the rebuild is done correctly. So what exactly is compression ratio? Well, a compression ratio compares the cylinder volume with the piston at bottom dead center to the cylinder volume with the piston at top dead center. Or, in simpler terms, compression ratio tells us how much the air is squeezed before fuel is injected. If you've watched some of my other videos, you've likely seen that diesel engines rely on heat from compression, not spark, for combustion to occur. Typical compression ratios for gasoline engines are roughly 8 to 1 to 11 to 1. Diesel engines, on the other hand, are in the range of 16 to 1 to 20 to 1. Diesels use higher compression ratios to ignite the diesel, which puts greater force on the piston, which can result in more power and torque, which heavy machinery needs. But how do we calculate it? Before we get to that, let's discuss two important related concepts. Number one is swept volume. This is the displacement of one cylinder. Displacement measures the space between when the piston is at the lowest point, or bottom dead center, and the highest point, which is top dead center. Number two is clearance volume. This is the volume of the combustion chamber when the piston is at top dead center. It's the space between the top of the piston and the cylinder head where the valves are located. And the formula we use to calculate compression ratio is compression ratio equals swept volume plus clearance volume divided by clearance volume, or compression ratio equals Vs plus Vc divided by Vc. Vs is the swept volume we just discussed, the displacement of one cylinder, and Vc is the clearance volume, combustion chamber volume at top dead center. Swept volume is calculated fairly easily, and clearance volume is determined by engine design. So how do we actually calculate swept volume? Well, the formula is Vs equals pi divided by 4 times bore squared, multiplied by the stroke. Some of you math fans might remember that the volume of a cylinder is pi r squared, and that's correct. But since we can get the bore diameter of the cylinder and the equation calls for the radius, we can simplify the equation of Vs equals pi times bore divided by 2 squared times the stroke to the one I first mentioned to try and keep the math as simple as possible. This swept volume formula calculates the volume the piston displaces as it moves from bottom dead center to top dead center. But enough math theory already, we'll now apply this to real engines. And we're going to start with the Cummins ISB 6.7 liter. These engines are in tons of larger pickup trucks, school buses, and medium-duty trucks. Here are a few specs of the engine that will help us with our calculations. There are 6 cylinders, the bore is 107 millimeters, the stroke 124 millimeters, total displacement, as you guessed, 6.7 liters, and the compression ratio is 17.3 to 1. But since we have these numbers, let's prove that math. First things first, we're going to have to convert to centimeters from the millimeter measurements given. Now there are 10 millimeters per centimeter, so we divide the bore and stroke measurements by 10 each to get the bore, which is now 10.7 centimeters, and the stroke, which is 12.4 centimeters. So let's plug our numbers into the formula we had earlier. Vs equals pi divided by 4 times 10.7 squared multiplied by 12.4 centimeters. This equals 0.7854 times 114.49 centimeters times 12.4 centimeters. This results in a volume, measured in cubic centimeters, of 1,115 centimeters cubed. This is the swept volume of one cylinder. But before we calculate the compression ratio, let's take a quick look at what we can do with this swept volume. Since we know from above that this engine has 6 cylinders, we can calculate the engine's total displacement. We do this by multiplying the swept volume of one cylinder, which we just calculated, by the number of cylinders the engine has. In this case, 1,115 centimeters cubed multiplied by 6. This equals 6,690 centimeters cubed. And since there are 1,000 centimeters cubed in a liter, we arrive at 6.690, which gets rounded up to 6.7 liters displacement. Hence, ISB 6.7 liter. But let's get back to this clearance volume calculation. Compression ratio equals Vs plus Vc divided by Vc. We have the compression ratio of 17.3 from our ISB 6.7 liter spec sheet, and we have our Vs or swept volume calculation of 1,115 centimeters cubed, which we just calculated. So 17.3 equals 1,115 centimeters cubed plus Vc divided by Vc. We're going to do some fraction math here to simplify things. Multiplying both sides by VC will result in a simplified formula. 17.3 VC equals 1,115 centimeters cubed plus VC. If we then subtract VC from both sides, we get a simpler formula of 16.3 VC equals 1,115 centimeters cubed. If we then divide each side by 16.3, we get VC by itself, with 1,115 centimeters cubed divided by 16.3. This final result is 68.4 centimeters cubed. But is this really important to me as a learning diesel technician? Well, yes, absolutely. These calculations are not things you need to do every day by any means, but understanding how these calculations are made helps you understand compression ratios and torque curves so much more. Let's go through another example quickly, this time with an older Navistar T444E 7.3 liter engine. These were found in late 90s, early 2000s school buses and a whole bunch of Ford Power Strokes. But let's start with the provided spec sheet again. Cylinders, there are 8 of them. Bore, 104.4 millimeters. The stroke, 106.2 millimeters. Total displacement, 7.3 liters, and a compression ratio of 17.5 to 1. Starting with the swept volume calculation, we have to first convert the bore and stroke to centimeters. The bore equals 10.44 centimeters, stroke equals 10.62 centimeters, and the swept volume, or VS, equals pi divided by 4 times bore squared multiplied by the stroke length, or pi over 4 times 10.4 squared multiplied by 10.5 centimeters. This results in a swept volume of 909.11 centimeters, which is also the displacement, again, of one cylinder. To calculate the total displacement, once again, we calculate the swept volume of one cylinder times the number of cylinders, which in this case is 8. 909 centimeters multiplied by 8 cylinders equals 7,272 centimeters cubed. Again, 1 liter equals 1,000 centimeters cubed for a total displacement of 7.272, which rounds up to 7.3 liters. But what does that 444 in the T444E even mean? Well, we can calculate the displacement in inches as well. So I'll give you one guess of what the displacement is for a T444 in inches. Okay, time's up. Yes, it is 444 inches cubed. Let's calculate that quickly with the same formula, just with converted centimeters over to the inches unit. Swept volume equals pi divided by 4 times 4.11 inches squared, multiplied by 4.18 inches. This results in a swept volume of 55.46 inches cubed. Now, if we multiply that by 8 cylinders, and we get 443.65 inches cubed, which rounds up to 444 cubic inches. Let's calculate that T444E clearance volume real quick as well. With a compression ratio of 17.5, let's fill in the formula to calculate for VC. Remember that compression ratio equals the swept volume plus clearance volume over clearance volume. We multiply each side by VC to end up with 17.5 VC equals 909.11 centimeters plus VC. When we subtract VC from both sides of the equation, we end up with 16.5 VC equals 909.11 centimeters. Then we divide 909.11 centimeters by 16.5 to get about 55 centimeters cubed for the clearance volume. All right, that was a lot of math, enough math for today. But let's think about engine rebuilds for a moment. Can an engine rebuild change compression unintentionally? This is where new technicians can get caught off guard. Even when a rebuild is done by the book, compression ratio may still change slightly. Common causes of this can include, number 1, head or block machining. This process removes material, small as it may be, which reduces the clearance volume, however. And a smaller clearance volume equals a slightly higher amount of compression. Number 2, head gasket thickness. Thicker gasket equals lower compression, as it slightly increases the swept volume compared with a thinner gasket, which will result in slightly higher compression due to a small decrease in the cylinder displacement. Number 3, aftermarket pistons. These may have different piston bowl shapes or volume, and small changes in piston bowl volume can make a big compression change. And number 4, deck height differences. All 3 of these previous changes affects the deck height. This is how far the piston sits below, flush, or above the block deck at top dead center. Any of these changes affects combustion chamber volume, which directly affects compression. But why does this all even matter? Well, higher compression can lead to harder cranking, along with higher cylinder pressures. Meanwhile, lower compression can result in hard starting, smoke, or power loss. This is why OEM specs and measurements matter during rebuilds, not just replacing parts. Now let's discuss compression ratio versus compression pressure, and make an important distinction between the two. The compression ratio is due to engine design, while compression pressure is the result of engine condition. Two engines with the same compression ratio can show very different compression test results, depending on piston ring seal, valve condition, cranking speed, and temperature. The compression ratio explains why diesel engines work the way they do, and we just learned why rebuild details matter more than people realize. But there's one diesel system that plays a big part in making sure your engine runs the way it should, so watch this video next to find out what it is.